When wiring a house without the AC condenser specifications, a useful rule of thumb can help approximate the necessary wire size. This rule suggests using 10 amps per ton for single-phase AC units. For 3-phase units, you can use 8 amps per ton. In the case of a 5-ton single-phase AC condenser, the approximate amperage can be calculated as follows: 5 tons multiplied by 10 amps per ton, which equals 50 amps. Given this approximation, a number 6 American wire gauge wire would be appropriate. However, it is crucial to consider several factors before making a final decision. Firstly, this rule of thumb is based on typical loads for central air conditioners. Actual amperage requirements can vary depending on the specific unit efficiency, SEER rating, and other factors. Always prioritize checking the manufacturer's specifications for the exact amperage, minimum circuit ampacity, and maximum overcurrent protection device size. This information is typically found on the unit's nameplate. Secondly, it is essential to adhere to local electrical codes and regulations. These codes provide guidelines for safe and compliant installations, including wire sizing, conduit requirements, and grounding practices. Consult the National Electrical Code, or NEC, and any local amendments to ensure compliance. Thirdly, consider the distance between the AC condenser and the electrical panel. If the distance is significant, voltage drop can become a concern. Voltage drop occurs when the voltage at the load, in this case the AC condenser, is lower than the voltage at the source, the electrical panel. Excessive voltage drop can lead to inefficient operation, overheating, and premature equipment failure. To mitigate voltage drop, use a larger wire size than initially calculated. The NEC provides guidelines for voltage drop calculations in Article 215.2 for feeders and Article 220.5 for branch circuits. Generally, a voltage drop of no more than 3% for the furthest run of the branch circuit to the AC condenser is recommended. The NEC provides tables and formulas for calculating voltage drop based on wire size, length of run, and current. Another factor to consider is the ambient temperature. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. High ambient temperatures can reduce the ampacity of a conductor, requiring a larger wire size. The NEC provides correction factors for ampacity based on ambient temperature in Table 310.13. If the AC condenser is installed in a location with high ambient temperatures, apply the appropriate correction factor to determine the adjusted ampacity of the conductor. The wire must be suitable for use in wet locations if installed outdoors. Use a wiring method approved for wet locations such as THWN or XHHW. If the AC condenser is located in a corrosive environment such as near the ocean, use a wiring method that is resistant to corrosion. In addition to wire size, the overcurrent protection device, such as a circuit breaker or fuse, must be sized appropriately. The overcurrent protection device is intended to protect the wiring from overloads and short circuits. The size of the overcurrent protection device should not exceed the ampacity of the wire. Consult the manufacturer's specifications for the maximum overcurrent protection device size. The NEC provides guidelines for overcurrent protection in Article 240. Grounding is another crucial aspect of AC condenser installation. Grounding provides a low impedance path for fault current to return to the source, helping to prevent electrical shock hazards. The AC condenser must be grounded in accordance with the NEC. Typically, a grounding electrode conductor is connected from the AC condenser to the grounding electrode system at the service. The size of the grounding electrode conductor is based on the size of the ungrounded conductors. The NEC provides guidelines for grounding electrode conductor sizing in Table 250.66. Furthermore, the AC condenser must be connected to an equipment grounding conductor. The equipment grounding conductor provides a path for fault current to return to the source in the event of a ground fault. The equipment grounding conductor must be sized in accordance with the NEC. The NEC provides guidelines for equipment grounding conductor sizing in Table 250.122. When selecting the wiring method, consider the environment in which the AC condenser is installed. If the wiring is exposed to physical damage, use a wiring method that provides adequate protection, such as rigid metal conduit or electrical metallic tubing. If the wiring is installed in a concealed location, such as within a wall, use a wiring method that is approved for concealed locations, such as non-metallic sheath cable or NM cable. In addition to the NEC, local codes may have additional requirements for AC condenser installations. Consult with the local electrical inspector to ensure compliance with all applicable codes. It is also advisable to consult with a qualified electrician to ensure that the AC condenser is wired correctly and safely. A qualified electrician has the knowledge and experience to properly size the wire, select the appropriate wiring method, and ensure that the installation complies with all applicable codes and regulations. In summary, while the 10 amps per ton rule provides a useful starting point for estimating the wire size for an AC condenser, it is essential to consider all relevant factors, including the manufacturer's specifications, local electrical codes, voltage drop, ambient temperature, and grounding requirements. Always prioritize safety and compliance when working with electricity. Remember to double-check all connections and test the installation before energizing the circuit. Taking these precautions will help ensure a safe and reliable AC condenser installation. When connecting the wires to the AC condenser and the electrical panel, use appropriately sized connectors. Connectors should be listed for the type of wire being used and should be installed according to the manufacturer's instructions. Ensure that all connections are tight and secure. Loose connections can cause overheating and arcing, which can lead to fires. After the wiring is complete, use a multimeter to test the voltage at the AC condenser. The voltage should be within the acceptable range specified by the manufacturer. If the voltage is too low, there may be a voltage drop problem. If the voltage is too high, there may be a problem with the electrical service. Also, use an amp meter to measure the current draw of the AC condenser. The current draw should be within the range specified by the manufacturer. If the current draw is too high, there may be a problem with the AC condenser. If the current draw is too low, there may be a problem with the wiring. Consider the future expansion of the electrical system when sizing the wire for the AC condenser. If there is a possibility that the AC condenser will be replaced with a larger unit in the future, it may be wise to install a larger wire size to accommodate the increased load. It is also essential to properly label all wiring and components. This will help to ensure that the electrical system can be easily maintained and repaired in the future. Use a permanent marker or label maker to label all wires, circuit breakers, and disconnect switches. The label should clearly identify the purpose of each component. When working with electricity, always wear appropriate personal protective equipment, or PPE, such as safety glasses and gloves. Never work on live electrical circuits. Always de-energize the circuit before working on it. Use a voltage tester to verify that the circuit is de-energized before touching any wires. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Electricity can be dangerous, and it is important to take all necessary precautions to avoid injury. In addition to the above, consider the following factors when sizing the wire for an AC condenser. Firstly, the type of wire. Different types of wire have different ampacities. For example, copper wire has a higher ampacity than aluminum wire. Secondly, the insulation rating of the wire. The insulation rating is the maximum temperature that the wire can withstand without degrading. Wires with higher insulation ratings can carry more current. Thirdly, the number of conductors in a raceway or cable. When multiple conductors are installed in a raceway or cable, the ampacity of each conductor must be derated. This is because the heat generated by the conductors can cause the temperature of the raceway or cable to increase. Fourthly, the soil conditions. The soil conditions can affect the ampacity of underground conductors. For example, conductors installed in dry soil will have a lower ampacity than conductors installed in wet soil. Fifthly, the altitude. The altitude can affect the ampacity of conductors. Conductors installed at higher altitudes will have a lower ampacity due to the reduced air density. Sixthly, the presence of harmonics. Harmonics are distortions in the electrical waveform that can cause conductors to overheat. If the electrical system is known to have harmonics, the wire size should be increased to compensate. Seventhly, the type of load. Some loads, such as motors, can draw a large amount of current when they start. This is known as inrush current. The wire size should be large enough to handle the inrush current. Eighthly, the power factor. The power factor is a measure of how efficiently electrical power is being used. Loads with low power factors draw more current than loads with high power factors. The wire size should be increased to compensate for low power factors. Ninthly, the harmonic distortion. Harmonic distortion is a measure of the amount of harmonics in the electrical waveform. High harmonic distortion can cause conductors to overheat. The wire size should be increased to compensate for high harmonic distortion. Tenthly, the imbalance. Imbalance is a condition in which the currents in the three phases of a three-phase system are not equal. Imbalance can cause conductors to overheat. The wire size should be increased to compensate for imbalance. Remember to consult the latest edition of the National Electrical Code, or NEC, for the most up-to-date information on wire sizing and electrical safety. And always prioritize safety when working with electricity.